everybody. Welcome to the Week 12 lecture. Let's just go ahead and get started. We're looking at a new type of integral today. So let's take a look. All right. Before we actually get into the integral, let's get a really quick vector review. So recall, if you have two vectors that are dotted together, one way to think of that is the length of the first vector times the length of the second vector times the cosine of the angle between them. So if this is vector u and this is vector v here, this angle right here would be the angle between them. Okay? And the length of a vector is positive. So really, if you get a positive or negative result from dotting two vectors, it's all due to the angle between them. So if you dot two vectors and get a positive number, that means that the angle between them is an acute angle. Because if you remember, if you have an acute angle less than 90 degrees, the cosine will always be a positive number. If, on the other hand, you get a negative number when you dot two vectors, let's look at that. That means my angle has to be out around here to get a negative, and that means that you have an obtuse angle. And if you dot two vectors and get something that's 0, that means that the vectors are perpendicular. So the angle is 90 degrees. All right? And we also looked at work being the force vector dotted with the distance vector. So you can see what happens if you're trying to move in one direction, but the force is going in an opposite direction. You're going to have negative work because that dot product will be negative. On the other hand, if you're moving in a direction and the force is in sort of the same direction, then you get positive work. And of course, if you're trying to move in one direction but the force is going the other, perpendicular to that, you're not going to have any contribution to that work. You're going to get 0 for the work done. So now let's look at this. Before we did this when we had a straight line, but now let's imagine that we're in the ocean and we've got a little kind of eddy here. So this is the current in an ocean, and you are starting here and you're moving, but you're not moving in a straight line. You're moving in a curve. So at every point along here, you've got these vectors that are working on the path that you're moving. So you're moving in this direction. All right. Now the force from this current is going to contribute to your path. So you've got some work done, some positive work done. And as you see, if you think about these little projections on here, you're getting positive numbers for the projections. You're getting, okay, so right here you've got an acute angle, you've got an acute angle like right through here, and so forth. There might be a spot along here where you've got maybe a perpendicular looking vector, but the current is contributing to the motion along here. So you're going to have positive work for the first example. And let's get another color. Come back here. For another example, maybe I'm traveling along this way. I'm starting here and moving along that way. And you can see the current is moving in a counterproductive manner. We're going against the current. That would be negative work done. All right. At each point on this path, I can think of a little tiny bit of work being done by the force from the ocean current as I go through. All right. Okay. So now let's talk about the type of integral we're talking about. These are called line integrals. And here's what we need to know for a line integral. First of all, we need to have a path that's oriented so we know which direction we're going on the path. A path, there's a path, As soon as I say which direction I'm moving on the path, now it's an oriented path. So I have a path along with a direction. I have a parametric equation for the path. And I have a vector field. Your vector field is going to act like the force, and the path is going to act like the distance. And then the line integral is the integral along the path of the dot product of the force with the derivative of the path, the differential of the path. Okay. Now, sometimes if the path is a closed curve, here's what a closed curve is it moves around, can be really complicated or very simple, and it ends where it starts. Ends and starts at the same place. If you have a closed curve, sometimes they put a little circle on here. They don't need to, but if you see that little circle, that's all it's telling you, is that you have added information that on your line integral, the curve happens to be a closed curve. And then some people call this the circulation of f over c. Now, how do we calculate these things? Actually, this is what we're doing along here. We're trying to figure out what the line integral would be. We're taking the dot product of the force vector, which happens to be the current vector in this case, with the direction vector, with the distance vector, which is the path. So let's talk about how to calculate these. The first thing you do is you find parametric equations for the r, for the path, and then you make a big substitution into the force vector, and you also find dr. And then it's just like a u substitution. So you take this complicated integral and turn it into a Calc 1 integral, actually. So here's an example. I've got a force vector, okay, x in the I direction plus y in the j direction. I have a line segment from 2, 2 to 6, 6. So I'm going to draw this path. I'm not going to try to draw the vector field, but it starts at the point 2, 2. And it ends at the point 6, 6. And we have a direction. It goes that way. So I'm going to get parametric equations for that path. In this case, the parametric equations are pretty easy to see. I could use t in the I direction plus t in the j direction, and t is the closed interval from 2 to 6. Okay, that's not the only parametric equation for this, but that's an easy one to use. And actually, as long as we have some parametric equation that's correct, we'll get the same answer. So if you come up with a different parametric equation for the path, you will still get the same thing in your line integral that I'll get, as long as it's a correct parametrization. All right? So here are 3 things I need to do. I need to plug t into f. I need to find dr. And then I need to just calculate. So here's how I do this. This is my x. This is my y. Okay, so my x here is going to be equal to t. F is equal to xi plus yj, and I know that x equals t from my parametric equations. And I also know that y is equal to t from my parametric equations. So I'm going to plug those both in for x. I'll have ti plus tj. The next thing I need to do is find dr. Well, that's easy to do. That's r prime times dt. So r prime is going to be 1I, taking the derivative of t, plus 1j. So there's my r prime dt. And the third thing I do is I calculate. So now I'm going to put it all together into the integral. So f is ti plus tj. I'm going to dot it, so there's my f. I'm going to dot it with my dr, which is 1 dt. And the last thing that I need are limits of integration, and those are the t values that make the endpoints of your path, so 2 to 6. And if I actually do the dot product, I'm integrating from 2 to 6. T times 1 is t. The other t times the other one is t. So I'm simply integrating from 2 to 6, 2t dt. And I know you know how to calculate that out, so I'll stop at that point. So 3 steps. After you get your parametric equations, you plug it into f to get your equation for f all in terms of t. You find dr by taking the derivative of r. Then you put it in the integral, crank it through, and you've got your answer. Okay? Let's do another example. Here I have f equals yi plus xj. C is the semicircle from 0, 1 to 0, minus 1, and x is greater than 0. So let's see, 0, 1 is here, 0, minus 1 is here, and we're using x greater than 0, so I'm going that way on my curve. So this looks like it could be a sine and a cosine, but I'm going the wrong direction. So since I'm going backwards, this is going to be cosine of negative t and sine of negative t. And t goes from pi over 2 to negative pi over 2. I can have time go backwards on these. They're fine. No problems. Okay. So let's get our equations. Whoops. The first thing I'm going to do is write my f. So f is y times I plus x times j, and the y is equal to sine of minus t. And the x is cosine of minus t. So there's my f. The next thing I'm going to do is find my dr. So I'm going to take the derivative of cosine of minus t, which will be minus sine of minus t times a negative 1 for a chain rule, which makes that a plus. And the derivative of sine of minus t will be cosine of minus t times negative 1 for a chain rule, so that becomes negative cosine of minus t. And I'll finish that with a dt because it's a differential, not a derivative. And now I'll put the whole thing together. I'm going to integrate from pi over 2 to minus pi over 2. No problem with that. Might seem a little funny looking, but it's fine. Of sine of minus t. Whoops, let me fix that. Sorry. Comma cosine of minus t. There's my f, dotted with my dr. dt. And let's multiply this through and see what we get. I'll have a sine squared of minus t. And then I'll have a minus cosine squared of minus t dt from pi over 2 to negative pi over 2. Okay, there are a couple things I can do to clean this up a little bit. Let's go to the next slide and take a look at that. Whoops, let me add a new slide in. So I had the integral from pi over 2 to minus pi over 2 of sine squared of negative t minus cosine squared of negative t dt. If that's correct, let me double check. Yeah. Okay, so let's see what we have here. If this were a plus, that would be easy integral to calculate, wouldn't it? But it's not. So one thing I'm going to see right here is I recognize that this is actually a double angle formula. Remember, we talked about this in class a couple times. The cosine of 2a is cosine squared of a minus sine squared of a. So this does look like a double angle. I'm going to rewrite it. Pi over 2 to negative pi over 2. I'm going to write it as negative cosine squared of negative t minus sine squared of negative t dt. And so that negative can come out. There's another thing that I can do. If you change the order of integration, which I'm going to do, that becomes a negative. So I'm going to have a negative from changing the order of integration, and I'm going to have another negative from factoring this negative out, and so that's going to become a positive. And I'm going to have cosine of 2 times negative t dt. So I've got negative pi over 2 to pi over 2 cosine of negative 2t dt. And I know that you can handle this one with a u substitution. du will be negative 2 dt. And when I plug in, and when t equals negative pi over 2, u is negative 2 times negative pi over 2 is pi. And when t is positive pi over 2, u will be negative pi. So this becomes from pi to negative pi. I've got those reversed again. Cosine of u times a negative 1/2, which I'll put out in front, du. And that I know you know how to calculate, so I'm going to stop there. Just wanted to also let you know that sometimes this is written as the integral of f times dx plus g times dy. And let's look at why that's true. Okay, so if my f is written as fg, so there's my vector field, and if my r is written as xy, then my dr is going to be the derivative of this, which will be x prime dx, y prime dy, just taking the derivative of each piece. And actually, let me not write x prime because it's a little confusing which variable we've got. Let me write dx dt and dy dt. But this whole thing is dx. Actually, that's a t. I'm so sorry. That's a t. This whole thing is dx. This whole thing is dy. And so if I'm going to integrate f dotted with dr, that's going to give me fg dotted with dx dy. And when I dot that out, that becomes f dx plus g dy. So same thing, just different notation. Just different notation. Okay. All right, let's look at one more example. So f is the log of y times I, log of x dx. I've got my c right here. There are my limits of integration between 2 and 4. So let's see what we get. When I plug in, I'm going to get the log of 2t. This is my new f. And when I plug in my, I'm sorry, I'm going to need to plug in y. So this will be the log of t cubed. And now I have log of x, so that'll be the log of 2t. My dr is going to be the derivative of c, which will be 2, 3t squared dt. And when I plug in, I'm going to have the log of t cubed, log of 2t, dotted with 2, 3t squared dt from 2 to 4, because those are my limits, which becomes from 2 to 4, 2 times log of t cubed plus 3t squared times log of 2t dt. Now, do you know how to integrate this? There are some techniques to integrate this. It's kind of nasty. Okay. I'm going to do a little bit of simplifying. The t can come out, the 3 can come out to get 6 log of t. And here I can break that into 2 pieces, but I'm going to leave that alone. 3t squared log of 2t dt. You can do integration by parts on this. It's nasty, but you can do it. And you can do integration by parts on this one as well. But instead of doing that, I'm going to show you a different technique in the next lecture. So this is it for now, but we're also going to have a part 2 and a part 3 to this lecture. And I'll see you in a little bit. Bye-bye.